Hi, everyone. Today we're going to discuss background radiation. Um, just a refresher on the electromagnetic spectrum. This shows the full breadth of electromagnetic radiation with, the gamma rays, X-rays, cosmic rays on the high end of the energy spectrum compared to, radio waves on the low energy end. Every one of these types of radiation here is present in the background level. There's at least some of this type of radiation everywhere on the surface of the Earth. Everyone will be exposed to ionizing radiation. That's the threshold above which the actual photons have enough energy to liberate electrons. That's sort of the threshold for biological damage. That is everywhere on Earth. Everyone is exposed to at least some radiation. So when people are absolutely terrified of ionizing radiation, it's important to remind them that they're being exposed to it all day, every day, and that certain diagnostic procedures, certain, casual contact with a therapy patient is not the end of the world. Does not mean that they are going to develop cancer because of that contact. You sometimes have to talk people down off of a ledge when it comes to ionizing radiation. So where does this background dose come from, specifically the ionizing radiation background dose? There's a number of places. From space. Space is a big one. There's lots of crazy, astronomical events taking place out in space that sort of shower the universe in radiation. And since the Earth is in in space, it gets, bathed in this radiation. So this can come in the form of actual, high energy photons just irradiating the Earth, traveling from, millions of light years away to fly through the atmosphere and interact with your body. That does happen. More often than not, though, this radiation comes in the form of high energy particle radiation that interacts with the atmosphere, and it creates somewhat of a cascade of radioactive particles that then shower down on the Earth. And you can either be exposed to these externally, or they have enough energy that they can actually activate, stable materials on Earth. And you can either ingest these, or they can directly activate them inside of your body. The most prominent being tritium and carbon-14, mostly because these have long half-lives. They're very abundant elements, but they also have very long half-lives, so they are created in enough of a volume that they're actually detectable. Other external sources, just inherent radioactivity in the ground. You have things like uranium, potassium, we discussed last class, I believe. Nuclear fallout during the arms race, the Cold War. There was lots and lots of atomic bombs tested above ground. These all released large amounts of radioactive material up into the atmosphere that slowly spread around the Earth. Some of these half-lives, the main fission products that are still with us have half-lives of roughly 30 years. So it's only been, 60, 70 years from that time period before they started to ban above ground testing. So there's still a lot of this material in the Earth, and whether that settles on the ground and externally irradiates you, or is actually picked up by plant life, by animals that are eating that plant life that we then consume. Those are all avenues for these trace amounts of radioactive materials to concentrate in your body, and they do give you dose. And then finally, one of the biggest ones is just the man-made X-ray radiation, predominantly in the use of the medical field. So getting to the actual, numbers, background exposure has been going up. A big part of that is from medical exposure. You have things such as CT scans, nuclear medicine procedures. These are incredibly valuable diagnostic tools, but they also come with a large dose of radiation sometimes. So if you look at the American population as a whole, there's people that are, cancer survivors that are getting CT scans every 6 months for the rest of their life, just to get out ahead of any sort of recurrence. They're going to get a large dose of radiation. The thought being that it's less harmful to them because generally these patients are older patients. There's a big latency period from radiation-induced cancers. If it is indeed a radiation-induced cancer, it's generally looking at 10, 15, 20 years later. So if you have a 70, 80-year-old cancer patient, you're not worried about the potential for a secondary cancer. You are worried about the cancer that they've just treated and potentially beaten coming back. So those CT scans, the dose is not really a concern. But if you look at it from a population standpoint, it's interesting to note that this radiation has been increasing. It's increasing to the degree that it's a pretty even split between man-made and natural sources, man-made being predominantly that medical exposure. The actual numbers break down to about 330 millirem each of natural and man-made sources. So that is summed up, that's about 660 millirem. And that has, like I said, that has been slowly increasing. On the natural side, you can see a large portion of the exposure from natural radiation is radon. We discussed this a little bit, how radon is an alpha emitting gas. So if you are in an area with radon, a lot of the country does have some degree of radon. You will have a large dose to your lungs, and that's why it takes up such a large piece of the natural side of the pie. Okay. It's important when you're dealing with background radiation to understand, the doses we're talking about. It's, 330 milligram is not a large dose. You could compare it to other, simple diagnostic procedures. These are listed here. These are useful rules of thumb to have in mind when you're discussing with a patient. Small doses from something like a chest X-ray. It's only chest X-ray is, 10 to 20 days of regular background radiation. So that makes it seem a little less intimidating. However, when you get into something like a CT and you're like, oh, well, it's equivalent to 2 years of background radiation, that starts to get to the point where maybe that's not as comforting, because, getting a 2 years of radiation dose in a single CT scan, and then someone starts to do the math of, wait, I'm getting CT scans every 6 months, then that could actually start to make them afraid. So you have to keep in mind when you throw these numbers around and comparing them to background, just how much background certain procedures can equate to. But to compare these numbers to actual deterministic effects, remember, deterministic are those threshold effects. So once you hit these limits, once you hit these numbers right here, that's when you expect to start to see some of these changes. So again, these are 1 to 2 orders of magnitude larger than even the highest on this chart. So you're not going to get a lot of these effects from basic diagnostic procedures, from background radiation levels. These are much, much larger doses that cause these sorts of issues. But remember, this is not the only effect from radiation. You also have those stochastic effects, which talk about raising your risk of cancer. And that's where those low doses are a little more of a gray area. They could be harmful, they could not. It's still, unfortunately, pretty unknown. So looking at the terrestrial sources of radiation, you have the cosmic sources that are reaching ground level, the uranium in the ground releasing radon gas, that's the big one. Also just industrial activities, mill tailings, that's the refinement of natural uranium into fissionable uranium for power production, for weapons. You also have coal power is one of the largest sources of radioactive material release in the country, something that doesn't get a lot of attention. And also just previous industrial uses, like the Manhattan Project, when the U.S. was rushing to build an atomic bomb, they kind of threw caution to the wind in terms of safety in a lot of ways. And there's large areas that were involved with the Manhattan Project that are contaminated to this day. They're starting to undergo remediation. We'll talk about things such as Superfund sites in later talks, but there are lots of areas that have been deemed unsafe for human occupation due to this work that's been done. So this is a map of terrestrial gamma ray exposure at 1 meter above ground. So this takes into account the inherent radioactive material in the ground, as well as sources such as cosmic exposure. And you can see that there's pretty large variations. There's a 2, 3, 4-fold increase in certain areas in background levels of radiation. So that just goes to show you that someone living in one of these pink areas where the background levels are 3 or more times higher than what we see on most of the eastern seaboard, you don't see excess cancers in these people, and there are people that are looking for this. So that's where it's important to note when you're talking to someone about low levels of radiation, that someone who lives in this pink area for their entire life will get 3 to 4 more times background radiation. So if you do the math of, okay, 600, 700 millirem a year times a 70, 80-year life, that adds up to real dose. But it still doesn't have enough of an effect to change that person's likelihood of developing cancer versus someone that grows up in a naturally low background area. Now, that's not to say it doesn't exist. It's not a large enough effect that it overcomes other confounding factors such as lifestyle choices, obesity, smoking, those things that really are known to have an effect on your lifespan. So it's thought that this effect is so low that you really can't even see it above the noise of all other sources. It's also important to keep in mind that the background rate of cancer just from living, just from all contributions of anything that could potentially cause cancer, it's something like 35 to 45% of people that are alive will develop some form of cancer in their lifetime. So trying to find something that raises that percentage 1% or 2% is a difficult task, because there's already such a high background incidence of cancer that to label something a radiogenic cancer, you really have to have a lot of concrete proof, and that so far that proof really doesn't exist. You'll see that these charts coincide pretty closely with areas of high potassium because of that small percentage of K40 being radioactive. Uranium concentrations also tend to be in the same areas, these high background areas. And then just the actual cosmic exposure. If we zoom in on our local area, you can see that these, there's no one level for an area. It's closer you zoom in, the more variation you get. It could really depend on the local geology down to your individual plot on a street. You can have radon testing in all the basements on a street and get vastly different numbers because of just the local conditions, like very, very local conditions where that house is built on. So, they have fancy instruments for making these maps, but the actual takeaways from the maps are a little less clear. So there is a certain amount of radioactive materials that is inherently in your body. The largest chunk of this is potassium-40, K40. This makes up roughly 1/100% of the natural potassium in the world. However, potassium is incredibly abundant in the Earth's crust. So it is an appreciable amount of radioactive potassium. In each individual person, there's about an average of 100 nanocuries per person. If you consume more potassium, you may be exposed to a little bit more from this pathway. But for the most part, this will make up the most dominant radioactive isotope in your body. And this is something that, nuclear power plants have very sensitive whole body scanners that are used to make sure no one's contaminated when you're leaving work for the day, or if you've been in a sort of an accident scenario. But these scanners need to have some sort of background subtraction for this content of potassium. Otherwise, they would give skewed results. Everyone would come up positive because 100 nanocuries is not a lot of activity, but for a very sensitive instrument, it is enough to get a very, very high reaction out of some instruments. I mentioned cosmic radiation. There's most of this radiation is in the form of particles. There is also photon radiation, but these particles, we talk about protons, neutrons, alpha particles, but a lot of cosmic radiation is actually super heavy ions, something like carbon ions, I think up to iron ions, or some of the most. So we talk about alpha particles having mass and charge and interacting very readily. Well, an iron nucleus stripped of all its electrons is much, much more massive than even an alpha particle, and it's much, much more charged. So that will just have, and it'll certainly react with the atmosphere, but it's essentially, an enormous cannonball hitting that atmosphere and just spraying a cascade of other radioactive particles down on the Earth. And It's also the energies we're dealing with are just energies that we can't even really comprehend on Earth outside of, the largest of linear accelerators where they're doing very novel, physics experiments. We're talking about, you know, giga EV, tera electron volts, orders of magnitude above the MeV that we're used to with our treatment machines or some, high energy decays. So the Earth, we have all these radioactive particles that are just flying through space everywhere. So how has life evolved on Earth to deal with this if there's so much radiation in space? And a big part of that is Earth's magnetic field. If you have charged particles that are flying around in space and you have a strong enough magnetic field, that magnetic field actually shields, it either catches or repels these particles, depending on the charge of the particles, and keeps them from actually bombarding the surface of the Earth and affecting us. So there's two radiation belts that were discovered. I forget when they were discovered. I think late 1800s, early 1900s. That there's essentially two rings of high densities of radioactive particles around the Earth that are essentially the Earth shielding them from interacting with us. But these, being on Earth, not an issue. But things like spaceflight, this is something that is a huge issue for spaceflight because the astronauts have to actually pass through these radiation belts to get anywhere in space. So the concern being, how much dose is this astronaut going to get passing through and coming back through these belts? And that's actually one of the most limiting factors for things like humans going to Mars. That is maybe the limiting factor, is that someone that takes a trip to Mars and back will get a dose of radiation. It's at least expected for them to get a dose of radiation that could have a significant effect on their lifespan, could lead to things like either temporary or permanent sterility. So other issues like this, it's not that people aren't willing to handle these effects. There's someone, you could probably have, a population of 7-8 billion, you'll find some people who are willing to throw caution to the wind and say, oh, I don't mind these effects. I want to be the first person on Mars. But, those aren't, one, they're not astronauts. And two, it's just seen as unacceptable risk. They're sort of waiting for newer technologies to figure out exactly how to make these less of a risk, novel shielding strategies. Lead and spaceflight don't really mix because it's such a struggle to get things off the ground that you need to limit weight as much as possible. But there are other novel materials that are in the works that can serve as very good shields for, these high energy particle radiations that may not need thicknesses of lead. They may just need some special type of material that can actually stop them or minimize their negative effects. So that stuff is in the works. We see some consequences of these radiation belts when we talk about things like the Northern Lights. These are actually instances where those particles get close enough to our atmosphere that they actually interact with the atmosphere. And that interaction takes the form of visible light and these very spectacular displays of light, mostly on the North Pole and the South Pole, because that's just where the curves of the magnetic field of the Earth sort of terminate. And the North Pole and the South Pole has significance from a magnetic field, not just a geographic location as well. So this is just a graphic of the inner belt and the outer belt, where they're most dominant and where they start to tail off, being on the North Pole and the South Pole. One area of radiation hazard that not a lot of people really comprehend is not spaceflight, is airplanes, is just air travel. For the casual traveler, it's not a huge deal. You figure when you're traveling on a plane, you're 7-8 miles in the air. You have less protection from the atmosphere, from radiation sources. That's a big reason why there's more radiation exposure. If you're someone that flies a couple times a week, it's a real concern, let alone the biggest risks being for pilots and flight crew. They are monitored to some extent, not nearly as heavily as in something like nuclear power or in the medical field. They're not regulated by something like the NRC or like, local government for radioactive materials licenses, because it's not. It's a natural source of radiation. It's just sort of a much higher natural source of radiation. So you have to be concerned about, pregnant pilots, pregnant flight crew. These are people that may exceed limits that are present in other fields, but because they're not limits in their field, they're not able to be protected by those limits. So that's something that is slowly coming into realization, but it does not have the level of regulation that something like our field does, or nuclear power. We talk a little bit more about man-made sources, especially from industry. If you couldn't tell, this presentation was made by someone that came from nuclear power, so they have a little bone to pick with coal power and exactly how much radioactive materials are released from coal. It absolutely dwarfs nuclear power. It's just nuclear power is so much more regulated, has so many more controls over what you can release to the environment, that makes the coal power just be such a dirtier, more contaminating source of radiation, even though its input is not truly radioactive material. You figure if you have coal coming from the ground, it's predominantly carbon, but there are trace amounts of other substances. And as that carbon gets burned away, you suddenly are left with a much more concentrated form of that other stuff. So if that other stuff is uranium and that other stuff is thorium or potassium, suddenly you have this modified material that can be very radioactive. It's what we call T-norm. It's technologically enhanced, naturally occurring radioactive material. There's something called norm, which is naturally occurring radioactive material, but something like this, where that most of the non-radioactive material is burned away, you can be left with very concentrated forms of radioactive material. And that's something that for right now is just released into the environment. Yeah, we all know that coal power is pretty dirty from a number of standpoints, but in the U.S. has a large supply of coal. It's sort of ingrained in our society that coal means energy independence. So it's something that's unfortunately a little bit more tolerated than something like nuclear power or even other forms of power generation. So other sources, Sloan Kettering itself releases radioactive material to the environment. We have a certain amount of effluence being release, whether it's stuff going up our smokestacks, going up the vents in the laboratories, have released to large plumes on the roof. As a little side note, this is unfortunately the class where we used to go up on the top of Zuckerman to show you some of the release points, and just taking the sites. Hopefully we'll be able to do that in the fall. That's something it's a very awesome place to be. I hope you guys get to see it. But yeah, we also release to the sewer system. We release a lot of material to the sewer system, but we also have tons and tons of water leaving our facility. So it's diluted to such a point that it's not really a hazard to anybody, but it's something that we have to track, and we have to tell the city how much we release and stay within our limits to make sure we're in compliance. Nuclear power is definitely a source of radioactive material being released into nature. It's much less because it's so closely regulated. Unless there is a disaster, then that is a huge source. But there's lots of design criteria to make sure that there's not a release. Just a quick overview on how nuclear power really works. You have the actual core right here that's creating all that heat from all the fission products. You have the primary loop that is pumping water through here. It's pumping water through here, super heated water that goes to this secondary loop. This heat is put into here, creates steam that drives the turbines, and then is cooled off by an actual outside source. That's why most nuclear power plants are built on bodies of water, whether it's the ocean or a river or a lake. They need a constant source of cooling water. So that's how it condenses back into water. It goes back into the steam generator. So these are two separate loops in order to minimize anything that is coming from here will not get into, an outside source of water. And there's many checks to make sure that doesn't happen. But sometimes, things break down. This loop may leak into this loop, and suddenly you have lots of radioactive material. But for the most part, it's a pretty reliable design. The actual process of refining uranium also creates a lot of low-level waste that mostly goes to storage yards, but also has the potential to leak into groundwater. Can have accidents that it releaks in much higher rates than others. What else? So one thing you may not realize is that there's lots of consumer products that contain small amounts of radiation. Again, going back to potassium, anything that has large amounts of potassium in it will be radioactive. There's a thing called no salt, which if you're trying to keep a low sodium diet, it's potassium chloride instead of sodium chloride. So this means that there's potassium in there, and that there's enough potassium to the point that if you actually held a radiation detector up to the no salt container in a grocery store, you would hear extra clicks on the radiation meter above background coming from the actual potassium. Another example is a smoke detector. If you actually take a smoke detector down from the ceiling and look on the back, you will see a radiation symbol, and you'll see that it's licensed by the NRC, and that something few people know is that when you buy a smoke detector, you are entering into what is considered a general license with the NRC, saying that you will not throw that in the garbage. If you get rid of it, you will not just toss it in the trash, because there is a small radioactive source in there that is used to detect the actual smoke. So they want to make sure that these aren't just getting dumped in the garbage. The same for tritium exit signs. There are exit signs that are not attached to external power. The thought being that if you have a power outage, you may need to get out of the building, but you won't have any lights. So what they do is they have large amounts of tritium in these signs, and they have that sort of radioluminescence. The tritium is decaying and creating a glow based off of some sort of fluorescent material inside the actual sign itself. Same idea, that if you buy these, you are entering into a license saying that you will not throw them out. So the regulatory oversight on a lot of these issues doesn't really fall to the NRC. So some are treated a little more serious than others. I mentioned the air travel, that's something that they're sort of catching up on. But they still have some means to do better. Coal plants, there's really not much consideration to the radioactive element, just because of there's such attention on the actual pollution element, on the carbon dioxide that's released, which is another negative for coal power. But it's here for the time being, at least. And then down to just someone like a licensee, like us, a medical licensee, that just has to keep their effluents to a minimum and make sure that they're not irradiating the people around them in their day-to-day work, which is something we take seriously. You hope that most licensees take it seriously. If not, that's where the inspection process comes in to really make sure that they're doing what they're supposed to. And that's it for background radiation. I will see you guys on Monday, and we can discuss more.